precisely 48 hours, an extraordinary event is set to unfold, the culmination of quiet preparations by NASA. An object, hurtling at 137,000 miles per hour from a distant stellar system, is scheduled to traverse a path just 29 million kilometers from Mars. However, there's a crucial detail being withheld from public knowledge. Dr. Avi Loeb, a distinguished figure from Harvard, has assigned this celestial body a rating of 6 out of 10 on his personal scale for the likelihood of harboring extraterrestrial technology. This translates to a 60% probability that its origin is not natural. Upon witnessing the images captured by amateur astronomers, you will comprehend the profound disruption gripping the scientific community. This is because its behavior deviates from that of any known comet. It is emitting pure nickel, conspicuously devoid of iron. This phenomenon is considered impossible within the natural realm. It exclusively occurs during industrial manufacturing processes. Its chemical composition exhibits 16 times the extremity observed in any previously documented comet. Furthermore, it underwent a radical color transformation, shifting from red to green overnight. Its trajectory also presents a mere 1 in 500 chance of being random. The situation becomes even more unsettling when considering that in late September, the object designated 3I Atlas will vanish behind the Sun for a period of 2 months. Consequently, it will remain unobservable during its closest approach to Earth on October 30th. Dr. Loeb has posited that this concealment may be deliberate, intended to evade scrutiny when the object is at its most luminous, or when another event transpires. Some scientists entertain the possibility that it may have already deployed minuscule, undetectable precursor probes, too small for terrestrial telescopes to discern, which could reach Mars while our attention is focused on the primary body. Over 227 observatories globally have been tracking this entity. They have meticulously compiled more than 4,000 individual observations, each contributing to its increasingly enigmatic profile. With an estimated mass of 33 billion tons, its existence defies current astrophysical understanding. The mathematical models simply do not align. We should have encountered 100,000 smaller celestial bodies before discovering one of such immense magnitude. Therefore, the fundamental question remains: what precisely is 3I Atlas? Within the next hour, I will meticulously present every anomaly, every leaked observation, and every theoretical framework that the scientific establishment is reluctant to publicly discuss. Because following October 3rd, when the spacecraft orbiting Mars turn their observational instruments towards this phenomenon, we may finally obtain definitive answers, or alternatively, encounter something far more disquieting. If your curiosity is as piqued as mine by this unfolding mystery, please engage the like button and subscribe. Furthermore, share in the comments section your current location, the local time, and the most unusual experience you have ever encountered. Chapter 1: Avi's astonishing 6 out of 10. Assessment. Dr. Avi Loeb has just undertaken an action that is sending tremors throughout the field of astronomy. This astrophysicist from Harvard, who previously suggested in 2017 that Oumuamua might represent alien technology, has now assigned 3I Atlas a rating of 6 out of 10 on his scale, gauging the potential for technological origins. This signifies a 60% confidence level that the object is not of natural genesis. Before you dismiss this assertion, it is imperative to understand the data that has swayed his perspective. This conclusion is not based on mere conjecture, but rather on empirical evidence gathered by the James Webb Space Telescope, the Very Large Telescope in Chile, and the Hubble Space Telescope, all of which have detected phenomena that defy conventional scientific explanation. On August 6th, the Webb telescope observed 3I Atlas and determined that its gas plume comprised 95% carbon dioxide and a mere 5% water. This ratio is 16 times more extreme than that of any known comet at comparable distances from the Sun. Comets are typically characterized by a substantial water content, a feature conspicuously absent in this case. Subsequently, the VLT detected the presence of nickel within the gas plume, evidenced by strong, unambiguous emission lines. However, here lies the most astonishing revelation. There was absolutely no iron detected. In the entire history of observing celestial objects, nickel and iron have invariably been found together. They are forged concurrently within the hearts of dying stars and are expelled together during supernova events. The detection of nickel without a corresponding presence of iron would be akin to observing smoke without any trace of fire. It simply does not occur in nature. Yet, it is a common occurrence in industrial manufacturing, particularly in the production of high-purity nickel alloys and aerospace components. The chemical signature precisely matches factory-produced materials, not cosmic debris. Moreover, the rate of nickel production is escalating. When first identified in July, the emission rate was moderate. By August, it had increased a staggering 25-fold. The closer it draws to the Sun, the greater the amount of metal being vaporized. Despite facing severe criticism for even entertaining extraterrestrial explanations, Dr. Loeb's findings are met with skepticism. Jason Wright of Penn State has characterized his work as sloppy, while Tom Statler of NASA maintains that the object exhibits characteristics consistent with a comet, performing typical cometary actions. However, neither of these explanations addresses the perplexing absence of iron alongside nickel, nor the extreme carbon dioxide ratio, nor the trajectory possessing only a 1 in 500 probability of being random. Dr. Loeb himself concedes that his technological hypothesis is largely an intellectual exercise, and that a natural comet remains the most probable explanation. Nevertheless, most probable does not equate to certainty. With his 6 out of 10 rating, he is indicating a 40% possibility that our current understanding is fundamentally flawed. The flyby of Mars on October 3rd is anticipated to provide further clarity. If the high-resolution imaging science experiment, HiRISE camera, reveals a nucleus exceeding 5 kilometers in diameter, as his mass calculations suggest, then the natural explanation will definitively falter. The current understanding of interstellar space does not account for a sufficient quantity of rocky material to account for such large objects appearing with such frequency. Chapter 2. The amateur photograph that captivated the Internet. Social media platforms are currently abuzz with images that professional astronomers are hesitant to engage with. Amateur astrophotographers are disseminating photographs of 3I Atlas that bear little resemblance to a typical comet. Instead of the diffuse, fuzzy glow one would expect, certain images reveal distinct structures, geometric forms, and sharp edges that should not be present. Michael Jagger and Gerald Raymond, 2 highly regarded amateur astronomers, managed to capture images of 3I Atlas during the total lunar eclipse on September 7th, observing from Namibia. These images depicted the object emitting a green light with a bluish hue, clearly indicative of a gas-rich composition, and it was discernible in both blue and green filter views. While professional astronomers have acknowledged the authenticity of these specific images, it is the contributions from other amateurs, whose names have not yet been featured in official press releases, that have generated what is now being referred to as the structured images. These photographs, circulating across platforms like Reddit, Twitter, and various astronomy forums, portray something more substantial and defined beneath the gaseous envelope, an entity that appears less like an amorphous cloud and more like an object with discernible edges. The reaction from the professional astronomical community has been characterized by either silence or immediate, outright dismissal. When pressed for explanations, they cite factors such as motion blur, exposure artifacts, and telescope tracking inaccuracies, all valid technical concerns when imaging rapidly moving objects that are thousands of times fainter than visible to the naked eye. Smearing and distortion are indeed common challenges. However, this is what makes the situation so intriguing. The Atlas Survey Telescope, responsible for the initial discovery of 3I Atlas, possesses a diameter of only 20 inches, a size comparable to equipment used by backyard astronomers. High-end hobbyists often possess comparable or superior equipment. Therefore, when individuals utilizing similar gear capture unusual structural details, why is there an automatic dismissal without any prior investigation? Debates are raging fiercely within Reddit's astronomy subreddits. Users are meticulously comparing images side by side. Some exhibit the classic cometary appearance, complete with a developing coma and a faint tail. Others, however, present features that are far more difficult to explain. Compact cores, irregular shapes, and pixel patterns that do not conform to the standard point spread functions typically associated with stars or comets. Approximately half of the commentators attribute these anomalies to image processing errors. The other half are vociferously demanding that professional astronomers, utilizing more advanced equipment, replicate these observations to either confirm or refute the findings. This verification process is conspicuously absent. Instead, professional astronomers are actively participating in online discussions, endeavoring to discredit the observations without offering to conduct their own independent checks. One image, widely circulated on X, appears to depict a more compact and less diffuse core than what was captured by the Hubble Space Telescope. The amateur who posted it claimed it was obtained using a 14-inch Schmidt-Cassegrain telescope by stacking 50 individual exposures, a standard procedure for deep sky imaging. Professional astronomers immediately attributed the unusual appearance to atmospheric distortion, tracking drift, chromatic aberration, or any other plausible explanation to rationalize it away. Crucially, none of them proposed directing larger telescopes towards the same celestial coordinates. None offered assistance in verifying the observation, opting instead for outright dismissal. Herein lies the peculiarity of this situation. The Hubble Space Telescope image acquired on July 21st revealed a teardrop-shaped envelope of dust, with the light extending forward from the object directly towards the sun. This is official NASA data, and it already defied expectations. Cometary tails are conventionally expected to trail behind, propelled by solar wind and radiation pressure. This particular object, however, was oriented forward. Professional astronomers described this observation as interesting, puzzling, and worthy of study. Yet, when amateur astronomers observe peculiar phenomena during the same time frame, it is immediately labeled as user error. Subsequently, the Gemini South Telescope captured images on August 27th, providing the first evidence of a discernible anti-solar tail extending behind the object. This suggests that between July and August, a significant change occurred. Either 3I Atlas began to behave more like a conventional comet, or our viewing angle shifted sufficiently to reveal features that were present all along. The majority of amateur photographs documenting unusual structures were taken during that critical July to August period when the object was exhibiting the least cometary behavior. a time when even professional observations revealed anomalies. Furthermore, there is another critical piece of data that warrants greater attention. NASA's Spitzer Space Telescope observed 3I Atlas in early August and detected it as a singular point source, devoid of any extended coma or tail, simply a distinct dot. This is not how comets typically appear in infrared observations. They usually display extended emission from warmed gas and dust. However, Spitzer observed nothing of the sort, only a single bright point. Therefore, a discernible pattern emerges. Professionals are observing anomalies that they cannot fully elucidate, while amateurs are observing phenomena that are readily dismissed as incompetence. Both are photographing the same object during the identical period of unusual behavior when it was not acting like a comet. The European Space Agency's Mars Express and ExoMars Trace Gas Orbiter are scheduled to photograph 3I Atlas on October 3rd, utilizing cameras designed to image the Martian surface from mere hundreds of kilometers away. They will be observing this object from a distance of 30 million kilometers. The ESA has already stated that spectacular images are not anticipated, as the object will likely appear as less than a single pixel within their camera's field of view. However, what if the amateurs were indeed observing something tangible? What if there is an underlying structure concealed within the gas? The October observations may not resolve this question either. It is possible that a closer approach, with more sophisticated instruments precisely aimed at the object without atmospheric interference, will be necessary. The reality is that our observations are partially obscured. Professional telescopes have limited allocated time and adhere to strict observation schedules. Amateurs, while possessing greater flexibility, operate with less advanced equipment. It is within this observational gap that something unusual is transpiring, something that neither group is fully prepared to acknowledge. Because if the amateurs are correct, and if there is indeed a structure that deviates from natural cometary morphology, then we are no longer discussing mere imaging artifacts. We are contemplating a fundamental rewriting of our understanding of interstellar visitors. Chapter 3. The October 3rd Mars Encounter. What they are not disclosing. In precisely 2 days, 3I Atlas will pass within 29 million kilometers of Mars. While this may seem like a considerable distance, the critical detail that remains unaddressed is the minimum orbit intersection distance. This represents the absolute closest the object will approach Mars' entire orbital path around the Sun, a mere 2.7 million kilometers. Dr. Avi Loeb has aptly described this proximity as remarkable fine-tuning. When a Harvard physicist employs such specific terminology, it warrants immediate and serious attention. The high-rise camera aboard the Mars Reconnaissance Orbiter will capture images of 3I Atlas with a resolution of 30 kilometers per pixel on October 3rd. This level of detail will be sufficient to differentiate the nucleus from its surrounding dust cloud. It will also be adequate to measure the actual surface area reflecting sunlight and, crucially, to confirm whether this object truly measures 5 kilometers in diameter, as suggested by Dr. Loeb's latest mass calculations. If its dimensions are indeed that substantial, the explanation of a natural comet will become entirely untenable. Based on the limited reservoir of rocky material available in interstellar space, we should have detected approximately 100,000 smaller interstellar objects akin to Oumuamua before encountering one as massive as 3I Atlas. Yet, we have only identified 2 previous interstellar visitors, both significantly smaller than this current object. However, the situation takes a genuinely unsettling turn when considering the implications of Dr. Loeb's calculations. He has posited that if 3I Atlas were to deploy a precursor probe, a smaller scout craft traveling approximately 30 million kilometers ahead of the main object. Such a probe could intercept Mars on October 3rd or during the week preceding it. The most chilling aspect of this scenario is that Earth-based telescopes are incapable of detecting objects smaller than roughly 100 meters at Martian distances. This size limitation is comparable to the largest spacecraft ever launched by humanity. Consequently, any precursor probe would be effectively invisible to us. This concept is not as far-fetched as it might initially appear. If one were tasked with designing an interstellar mission to survey a planetary system, the most logical approach would not be to send a single, massive vessel. Instead, one would deploy a mothership accompanied by smaller reconnaissance probes. These probes would be released in advance to gather data on individual planets, while the primary craft maintained a safe trajectory through the system. This is precisely how such a mission would be engineered if we possessed the necessary technology. The trajectory of 3I Atlas renders this scenario disturbingly plausible. The object's path necessitates only a minor velocity adjustment of 10 to 15 kilometers per second during September to reduce its closest approach to Mars to zero. For a technologically advanced object, this maneuver would be trivial. For a natural comet, however, it is impossible. Based on data from the Webb telescope, the ejection velocity of icy fragments from sublimating comets is only around 0.4 kilometers per second, which is insufficient. NASA's Mars Express and ExoMars Trace Gas Orbiter will also be observing 3I Atlas on October 3rd, employing a suite of instruments including high-resolution cameras, spectrometers, and particle sensors. While these instruments are primarily designed for studying the Martian surface and atmosphere, they are being repurposed to examine this interstellar visitor. The instruments will endeavor to characterize the comet's volatile activity and its chemical composition from a distance of 30 million kilometers. However, there exists a secondary objective that is not being openly publicized. The ExoMars orbiter will not solely focus on imaging 3I Atlas. It will also scan the surrounding space, searching for any entities that might be preceding the main object, essentially looking for precursor probes. Dr. Loeb explicitly suggested this in his blog posts. Use HiRISE to search for objects preceding 3I Atlas that get closer to Mars than the main body. The rationale is that if materials originating from 3I Atlas reach Mars in October, and these materials could not have naturally arrived through sublimation and ejection, it would serve as a definitive signature of technology. The timing of these events is also conspicuously suspicious. 3I Atlas will achieve its closest proximity to Mars precisely 1 week before it disappears from Earth's vantage point behind the Sun. This provides us with a single opportunity for detailed observation via spacecraft near Mars, after which the object will vanish into solar glare for a full 2 months, remaining unobservable until early December. If one intended to deliver an object to Mars covertly, this time frame would represent the ideal window. A probe could be deployed during the October 3rd flyby, while Earth's telescopes are focused on the primary object. Subsequently, the mothership could take refuge behind the Sun for 8 weeks while the probe carries out its clandestine mission. NASA's Curiosity and Perseverance rovers, situated on the Martian surface, may also attempt observations. Although the comet will be exceedingly faint from a surface perspective, the Mars Reconnaissance Orbiter remains our most promising tool for obtaining detailed imagery. And then there is the profound question of what actions would be taken if something were discovered. If the HiRISE camera were to capture images revealing multiple objects, unusual maneuvering, or any indication of artificial activity, What would be the established protocol? Would an immediate announcement be made? Would further observations be conducted for verification? Would the information be classified? There is no predefined procedure for such a scenario because no one has seriously prepared for it. Current protocols for detecting extraterrestrial intelligence primarily focus on radio signals or optical beacons, not on the physical transit of craft through the inner solar system. Within 24 hours, we will ascertain whether the amateur astronomers were observing something genuine. We will discover if the nickel without iron signature holds the significance that Dr. Loeb believes it does. We will determine if the 2.7 million kilometer minimum orbit intersection distance was a mere coincidence or a deliberate design. Alternatively, we may witness the passage of a perfectly ordinary cometary nucleus, consistent with natural formation, and all speculation will dissolve into an embarrassing miscalculation. Regardless of the outcome, October 3rd, 2025, is a date that may well be etched into history books. The day on which we either confirmed 3I Atlas as an exotic yet natural interstellar comet, or the day when everything irrevocably changed. Chapter 4. The Nickel Without Iron Revelation. The Very Large Telescope in Chile has just made a detection that defies natural explanation. Between late July and late August of 2025, spectroscopic analyses revealed the presence of neutral nickel atoms emanating from 3I Atlas. These findings were characterized by strong emission lines across multiple wavelengths, providing clear and unambiguous evidence of nickel sublimating from the object's surface as it approached the Sun. However, conspicuously absent was any trace of iron. Not a single emission line was detected at any of the expected wavelengths where iron should have appeared. It is crucial to understand why this observation is profoundly shocking. Nickel and iron are intrinsically linked in the cosmos. They are synthesized together through the same nuclear fusion processes within massive stars. When these stars subsequently explode as supernovae, nickel and iron are expelled into space in tandem. They then condense into dust grains collectively and are incorporated into asteroids and comets as a unified component. In every single celestial rock that humanity has ever analyzed, whether meteorites that have fallen to Earth or samples retrieved from space missions, nickel and iron consistently appear in predictable ratios. Discovering one element without the other would be analogous to finding hydrogen devoid of protons. It fundamentally contradicts the established chemistry of the universe. The research team at the VLT, comprised of scientists unaffiliated with Dr. Loeb's more controversial hypotheses, published their findings with meticulously chosen phrasing. They suggested that the nickel might originate from nickel carbonyl compounds, molecules theoretically capable of existing in extremely frigid interstellar environments. These compounds are volatile and are known to dissociate when exposed to ultraviolet radiation, releasing nickel and carbon monoxide. Nevertheless, even the VLT team acknowledged that such an occurrence would be unprecedented. It has never been observed in any solar system comet, nor has it ever been detected in interstellar space. A purely theoretical explanation, advanced for an observation that demands one. The situation is further exacerbated by the fact that the nickel production is not constant. When 3I Atlas was initially observed at a distance of 3.9 astronomical units from the Sun in July, the rate of nickel emission was approximately 10 to the 21st power. While significant, it was not yet considered alarming. By late August, at a distance of 2.85 astronomical units, that rate had escalated by a factor of 25. This indicates a 25-fold increase in the amount of nickel being released from the object's surface within a single month. The closer the object draws to the Sun, the more dramatically its metallic emissions intensify. This acceleration does not follow the gradual curves typically observed with natural cometary outgassing. Instead, it is exponential and steep, suggesting a systematic vaporization driven by increasing heat. Dr. Loeb articulated what others have been reluctant to state explicitly. On Earth, we routinely separate nickel from iron through industrial processes. High-purity nickel is utilized in specialized alloys for applications in aerospace, electronics, and battery technology, wherever specific thermal or electromagnetic properties are required. The signature detected from 3I Atlas aligns precisely with industrial nickel production, not with naturally occurring cosmic abundances. Critics were quick to seize upon this point, accusing Dr. Loeb of selectively presenting data, engaging in confirmation bias, and pursuing motivated reasoning. Jason Wright of Penn State was particularly critical, deeming the comparison to industrial processes to be misleading and unscientific. However, the critics have failed to address a critical point. If the nickel is indeed derived from natural carbonyl compounds, then where is the iron? Iron also forms similar volatile compounds. Iron pentacarbonyl is a well-studied chemical entity. If the conditions were sufficiently conducive to create and preserve nickel carbonyls over billions of years in interstellar space, those same conditions would undoubtedly have facilitated the creation of iron carbonyls. Both should be present, yet only nickel is being detected. The VLT observations also indicated a rapid increase in cyanide production, with hydrogen cyanide and related compounds appearing in the gas plume surrounding 3I Atlas at rates that steeply rose as the object approached the Sun. Dr. Loeb has suggested that the observed color change from red to green by amateur astronomers might be linked to this surge in cyanide levels. While cyanide itself is not an unusual component of comets, it is a common carbon and nitrogen compound found in many icy bodies. The rate of its increase, the steep production curve that mirrors the nickel emissions, suggests a potential interconnectedness between these processes. What's truly remarkable is what this reveals about the object's elemental makeup. If the bulk of its mass is composed of frozen carbon dioxide, with only minute traces of water as Webb identified, and if its surface is emitting nickel and cyanide at escalating rates, then we are observing a chemical profile that does not align with anything formed within our solar system. Comets originating from the Oort cloud or the Kuiper belt are abundant in water because they coalesced in an environment where water ice remained stable. The proportions of water to carbon dioxide reflect the temperature and composition of the primordial disk from which they emerged. 3I Atlas, however, exhibits the inverse ratio. It is predominantly carbon dioxide with minimal water content. This suggests it formed in a drastically different environment, orbiting a vastly different star. Alternatively, it implies it may not be a natural celestial body at all. There exists a third possibility, one that few are inclined to seriously consider. What if 3I Atlas is indeed a natural entity, an ancient comet from another star system, but one that has traversed interstellar space for such an extended period that its surface chemistry has been significantly altered? The impact of cosmic rays, collisions with interstellar dust particles, and chemical reactions in the near absolute zero vacuum over 7 billion years of exposure could profoundly modify its surface composition. It's conceivable that the observed signature of nickel without iron is genuine, but its explanation lies somewhere on the spectrum between a natural comet and an artificial construct, something beyond our current comprehension because we have never before examined an object of such antiquity from such a vast distance. The observations scheduled for October will be crucial, particularly when the HiRISE instrument on the Mars Reconnaissance Orbiter captures images of 3I Atlas from Martian orbit. Spectroscopic data gathered by the Mars Express and ExoMars Trace Gas Orbiter spacecraft will detect additional emission lines, providing more insights into the nickel production, more precise measurements of the cyanide and carbon dioxide outgassing, and further constraints on the true nature of this object. However, based on the data currently available, 3I Atlas is dispersing industrial-grade nickel into space, exhibiting no detectable iron. Consequently, no one has a fully satisfactory natural explanation for this phenomenon. Chapter 5. The Vanishing Act, Concealed by the Sun. In late September, 3I Atlas disappears from view. It is not destroyed, nor is its trajectory altered. It is simply obscured. From Earth's perspective, it passes too close to the Sun to be observed. For a period of 2 months, from late September through November, ground-based telescopes lose all line of sight. The object is lost within the Sun's intense glare. What makes this timing particularly suspicious is that 3I Atlas reaches perihelion, its closest point to the Sun, on October 30th, 2025. This is the precise moment when comets are at their most active, when solar heating maximizes their outgassing, and when their behavior reveals the most about their composition and structure. This constitutes the single most critical observational window for understanding the object's true nature, yet we are unable to see it. Earth will be positioned on the opposite side of the Sun. Avi Loeb has posited that this celestial alignment could be deliberate, not a random occurrence of orbital mechanics, but a precisely planned maneuver. If 3I Atlas intended to evade detailed scrutiny from Earth-based telescopes during its brightest and most active phase, its current trajectory achieves exactly that. It effectively hides behind 150 million kilometers of incandescent plasma at this critical juncture. NASA and other space agencies are endeavoring to circumvent this limitation. The Parker Solar Probe, presently in close solar orbit studying the Sun's corona, might potentially capture a glimpse if its timing is fortuitous. The Solar and Heliospheric Observatory, SOHO, which continuously monitors the Sun for coronal mass ejections, will have 3I Atlas pass through its field of view. However, SOHO's cameras are engineered for solar observation, not for detecting faint comets. The object is likely to be too dim against the overwhelming brilliance of the Sun. The Jupiter Icy Moons Explorer, JUICE, is currently on the far side of the Sun relative to Earth. It is utilizing its high-gain antenna as a heat shield, which consequently limits its data transmission capabilities. JUICE will attempt to observe 3I Atlas in November using its cameras and spectrometers, but the data will not be received until February 2026, months after the observations have been made. Thus, we are effectively blind during the most crucial period. The events of October 30th will unfold behind a stellar curtain, and what might transpire during those 2 months? If 3I Atlas is a natural object, nothing unexpected should occur. It will increase its outgassing due to heating, and it may fragment if thermal stress cracks its nucleus. Upon emerging in December, it will be slightly smaller and less active as it resumes its journey back into interstellar space. However, if it is not natural, if it possesses any technological component, those 2 months represent the perfect interval for activities that we are not intended to witness. This could include orbital adjustments, the deployment of probes, trajectory modifications, or any maneuver requiring propulsion or significant directional changes that would be readily apparent to Earth-based observers if they could see it. Loeb calculated that a velocity alteration of merely 10 to 15 kilometers per second during September or October could substantially alter 3I Atlas's trajectory to the extent that it could deliver payloads to Mars, Venus, or even Earth. For a natural comet, such a feat is impossible, Sublimating ice generates velocity impulses of perhaps half a kilometer per second at most. However, for an object equipped with an engine, this is a trivial matter. A more unsettling possibility exists. What if the disappearing act is precisely that, a disappearance? What if 3I Atlas does not reappear in December? What if it leverages its perihelion passage to decelerate, enter a prolonged elliptical orbit around the Sun, and become a permanent resident of the inner solar system? We would have no way of confirming this until December, when it is expected to re-emerge. And if it does not appear where calculations predict, if its orbit has undergone substantial alteration that would unequivocally indicate the presence of propulsion, technology, and intent, there is a precedent for such speculative thinking, although not with interstellar objects. In 1986, the Soviet Vega probes flew past Halley's Comet and detected something unexpected. The nucleus was considerably darker than anticipated, reflecting only 4% of incident sunlight. Prior to the Vega missions, scientists had assumed comets were luminous, icy bodies. It turned out they are extraordinarily dark, covered in organic compounds and dust, with the ice buried beneath a crusty surface layer. That revelation fundamentally altered our understanding of what comets look like up close, and it was discovered because we dispatched spacecraft to investigate. Remote observations from Earth had led us to entirely erroneous assumptions. With 3I Atlas, we are once again reliant on remote observation during a critical period, inferring behavior from limited data and making assumptions that could prove completely inaccurate. We will not know the truth until December 3rd, when it emerges from behind the Sun and becomes visible once more to ground-based telescopes. Amateur astronomers are already preparing for this event. Telescopes across the globe are being scheduled for early December observations. Everyone is eager to be the first to spot its return. Everyone wants to ascertain if it appears different, if its activity level has changed, or if its trajectory aligns with predictions. Because if it does not align, if 3I Atlas emerges from perihelion on a divergent path or with altered characteristics, that is the moment when the mainstream astronomical community will be compelled to seriously consider the artificial hypothesis, not as a fringe theory championed by a single controversial scientist, but as a legitimate possibility demanding thorough investigation. The disappearing act also means we miss potential fragmentation events. Natural comets occasionally disintegrate near perihelion due to thermal stress fracturing the nucleus. Internal pressure from trapped volatiles can eject fragments from the surface. We have witnessed this phenomenon with several comets that ventured too close to the Sun. If 3I Atlas fragments, we will not observe the event itself. We will only see the aftermath in December. Multiple pieces instead of a single entity, debris trails, altered rotation, and fragmentation would, in fact, support the natural comet hypothesis. Technological objects do not typically fracture due to solar heating, unless, of course, the fragmentation is controlled, and what we perceive as a breakup is actually a deployment, with multiple smaller objects separating from the main body, each proceeding towards different destinations within the inner solar system. That scenario sounds like pure science fiction, yet so does nickel without iron. So does the perfect alignment with the ecliptic plane. So does the flyby of Mars, with an accuracy of 2.7 million kilometers. Each piece of data we gather renders the science fiction scenarios progressively less fictional. The December reappearance will provide us with some answers, perhaps not all, but certainly something. Until then, we wait in the darkness, hoping that the object which reemerges is the same one that vanished behind the Sun. Chapter 6. The anomalously massive object. 33 billion tons. A recently published paper is causing considerable unease among astronomers. Richard Chloe, Peter Vey, and Avi Loeb have analyzed 4,022 observations of 3I Atlas, conducted by 227 observatories worldwide between May 15th and September 23rd. They meticulously tracked the object's position, comparing its actual trajectory with the path predicted by gravity alone. Their findings were astonishing. 3I Atlas exhibits almost no non-gravitational acceleration. Despite the substantial outgassing detected by Webb and other telescopes, and despite losing hundreds of kilograms of material per second, the object's trajectory deviates by less than 15 meters per second, squared from a path determined solely by gravity. This implies it possesses an immense mass, far exceeding what its brightness would suggest. The mathematical reasoning is straightforward. When a comet releases gas, the expelled material functions as a miniature rocket engine, subtly altering the comet's course. The magnitude of this deviation depends on the quantity of mass being expelled and the comet's own mass. Small comets with vigorous outgassing exhibit significant non-gravitational acceleration. Larger comets with equivalent outgassing display less deviation. 3I Atlas is expelling substantial volumes of gas. Webb measured 129 kilograms per second of carbon dioxide, 6.6 kilograms per second of water, and 14 kilograms per second of carbon monoxide. These are considerable quantities, and they should induce noticeable changes in trajectory. However, they do not. The deviation falls below detection limits, indicating that the object's mass must be enormous to counteract the thrust generated by this expulsion. Calculations place the lower limit of its mass at 33 billion tons, equivalent to 33 trillion kilograms, with a nucleus diameter of at least 5 kilometers. This renders 3I Atlas 3 to 5 orders of magnitude more massive than the two previous interstellar objects discovered. Oumuamua was perhaps a few hundred meters across at most, and Borisov was possibly a kilometer in size. This object is 5 times larger in diameter, translating to over 100 times its volume and mass. Herein lies the problem. Based on our understanding of interstellar space and surveys of the abundance of rocky and icy material between stars, objects of this magnitude should be exceedingly rare. They should be so scarce that we would expect to detect roughly 100,000 smaller interstellar visitors before encountering one as massive as 3I Atlas. Yet, we have only identified 2 such objects in the entire history of human observation. It is akin to winning the lottery 3 consecutive times, statistically possible, but so improbable that one begins to question the integrity of the game itself. Loeb argues that this points towards a non-random trajectory. If 3I Atlas was deliberately directed towards the inner solar system, if its path was a chosen one rather than a random occurrence, then the statistical anomaly dissolves. We are not merely sampling the interstellar population randomly. We are being visited by something specific. Critics dismiss this assertion as preposterous. They highlight the dramatic improvements in our detection capabilities in recent years. The Atlas survey, which discovered 3I Atlas, only became fully operational within the last decade. Prior to that, our observational efforts were simply insufficient. It is therefore unsurprising that we are now discovering more interstellar objects. We finally possess telescopes capable of detecting them. This is a valid point. The Vera C. Rubin Observatory, which commenced operations in 2025, identified over 2,000 asteroids within its first 10 hours of activity. Our capacity to detect faint, rapidly moving objects has surged exponentially. It is plausible that we will discover dozens more interstellar visitors in the coming years, thereby resolving the statistical issue. However, this does not account for the mass. Even with enhanced detection capabilities, and even if we discover more interstellar objects, their size distribution should conform to predictions. Numerous small objects, fewer medium-sized ones, and a very limited number of large ones. This is how populations function throughout the astronomical universe. Small asteroids vastly outnumber large ones by millions to one. 3I Atlas defies this pattern. It is by far the largest object we have encountered, discovered before we have catalogued the thousands of smaller objects that should be more prevalent. Furthermore, the absence of significant non-gravitational acceleration precludes certain explanations. Some scientists have suggested that 3I Atlas might be a loosely aggregated rubble pile, held together by weak gravitational forces. If this were the case, the process of outgassing would cause it to disintegrate. The propulsive forces generated by the expelled material would overcome the gravitational binding, leading to fragmentation. Yet, it is not fragmenting. It is maintaining its structural integrity despite substantial mass loss. This suggests either a solid, coherent nucleus or a binding mechanism more effective than self-gravity. The observations from Mars scheduled for October could clarify the size enigma. If HiRISE can successfully differentiate the nucleus from its surrounding dust cloud and measure the light reflected by the solid surface versus that scattered by ambient particles, we will obtain a more accurate estimate of the true nucleus diameter. If it exceeds 5 kilometers, the natural explanation becomes increasingly untenable. An additional possibility, which has received limited attention, warrants consideration. What if 3I Atlas is enveloped by a vast, diffuse cloud of extremely fine dust, and the majority of the observed brightness originates from this dust rather than the nucleus itself? In such a scenario, the nucleus could be significantly smaller, rendering the mass calculations inaccurate. However, both Webb and SphereX observed the object in infrared wavelengths. Infrared radiation penetrates dust, revealing solid surfaces beneath. SphereX detected 3I Atlas as a point source, not an extended cloud. This indicates that there isn't a substantial dust envelope obscuring a diminutive nucleus. What we are observing is predominantly the object itself. Therefore, we return to the conclusion of a 5-kilometer nucleus with a mass of at least 33 billion tons, exhibiting virtually no non-gravitational acceleration despite significant outgassing. This represents an object that, statistically, should not exist. It arrived on a trajectory with only a 1 in 500 chance of being random. The accumulation of data continues, with each observation making the natural explanation increasingly improbable. Not impossible, but progressively contrived, necessitating more and more special pleading, a greater number of coincidences, and a series of unprecedented conditions. Chapter 7. Chemical Impossibilities, the 95% CO2 Mystery. The James Webb Space Telescope observed 3I Atlas on August 6, 2025, utilizing its near-infrared spectrograph. The findings from this observation fundamentally challenge our understanding of what interstellar comets should resemble. The gaseous plume surrounding 3I Atlas is composed of 95% carbon dioxide and only 5% water. This ratio is 16 times more extreme than what would be expected for a typical comet at that distance from the Sun. Every comet we have ever studied within our solar system is water-rich. They formed in the frigid outer regions where water ice was the dominant volatile compound. Carbon dioxide is also present, but in significantly lesser quantities. This ratio serves as an indicator of the temperature and chemistry of the protoplanetary disk from which they originated. 3I Atlas displays the reverse chemistry. It is essentially a dry ice ball with a minimal amount of water. This strongly suggests it formed in an environment vastly different from our own, orbiting a star with a distinct composition, within a disk characterized by different temperatures and pressures, an environment wholly unlike the formation conditions of our solar system. Martin Cordner, the principal investigator for the Webb observations, stated, "This represents one of the highest carbon dioxide to water ratios ever measured in any comet, not merely unusual, but unprecedented." However, the chemistry becomes even more perplexing. Webb also detected significant quantities of carbon monoxide and carbonyl sulfide. The coexistence of these compounds implies that the object coalesced in an extremely cold environment, potentially colder than the outermost reaches of our solar system. Some researchers propose that 3I Atlas may have originated in a molecular cloud region, or been ejected from a planetary system situated much farther from its star than our Kuiper belt. Furthermore, amateur astronomers documented a striking color change. In July and early August, observations indicated that 3I Atlas possessed a reddish coma. This coloration typically signifies the presence of organic compounds, complex carbon molecules that absorb blue light and reflect red light, a common characteristic of comets. However, on September 7th, during a total lunar eclipse, Michael Jagger and Gerald Raymond captured photographs of it, glowing a vibrant green with a bluish tinge. This transformation apparently occurred overnight. Green comets are a well-known phenomenon, with the color originating from diatomic carbon molecules in the coma that absorb ultraviolet sunlight and re-emit it as green light. Curiously, 3I Atlas had already been analyzed in August by astronomers at the Kitt Peak Observatory. They determined that it was among the comets with the lowest carbon chain depletion known, exhibiting very low concentrations of diatomic carbon, the very molecule responsible for producing green comets. Therefore, how could a comet with virtually no diatomic carbon suddenly emit a brilliant green luminescence? Avi Loeb suggested that the color change might be linked to the rapid surge in cyanide production detected by the Very Large Telescope, VLT. Cyanide compounds can also produce greenish hues under specific conditions. But this raises another pertinent question. Why is the production of cyanide escalating so dramatically? The VLT observations revealed a steep increase in hydrogen cyanide emission as 3I Atlas approached the Sun. The rate of production was not gradual, as is typical for cometary outgassing. It was exponential, suggesting something was undergoing thermal processing at accelerating rates. Stephanie Milam from NASA's Goddard Space Flight Center, who collaborated on the Webb observations, theorized that 3I Atlas might possess a cooked outer shell. Billions of years of travel through interstellar space, exposed to cosmic rays and stellar radiation, could have chemically altered its surface layers. Carbon dioxide may have been created or concentrated through these processes, resulting in its unusual surface chemistry. This explanation is plausible. We have never before studied an object of such immense age. 7 billion years is older than our entire solar system. It is difficult to fathom what might happen to ice over such a timescale in the near absolute zero void between stars. However, this does not account for all the anomalies. The signature of nickel without iron is not explained by surface processing, nor is the lack of significant outgassing. While each individual anomaly might possess a natural explanation, their collective presence forms a pattern that becomes increasingly challenging to dismiss. Additionally, the Spherex observation, which showed 3I Atlas as a point source with no extended emission, warrants attention. Infrared telescopes can penetrate dust to reveal the thermal emissions from warming ice and rock. Spherex should have detected a diffuse glow emanating from carbon dioxide ice sublimating across the surface. Instead, it observed a pinpoint, a concentrated source of infrared emission consistent with a relatively compact solid object. This observation contradicts the prevailing comet model, or it suggests that the object possesses highly unusual thermal properties. Perhaps its surface is extremely reflective, deflecting sunlight before it can heat the interior. Alternatively, an insulating layer might be preventing heat penetration. It is also possible that the nucleus is spinning so rapidly that thermal energy is distributed before significant sublimation occurs. Or perhaps it is not outgassing in the manner we currently understand it. Perhaps what we are interpreting as sublimation is, in fact, something else entirely. The chemical data also provide insights into 3I Atlas's potential origin. Its low metallicity and high hydrogen and ice content suggest it originated from a region of the galaxy where star formation occurred early, specifically the thick disk of the Milky Way, populated by older stars with less heavy element enrichment. Scientific estimations place its genesis somewhere between 7 and 11 billion years in the past, originating from an era when our cosmic neighborhood was vastly different. If 3 Atlas is a natural celestial body, it represents a time capsule from the ancient galactic expanse. It's akin to a fragment of primordial ice, carrying chemical imprints from epochs preceding Earth's formation by billions of years. This alone would elevate it to the status of the most scientifically significant object ever encountered. However, its chemical composition persistently defies easy categorization. The prevalence of carbon dioxide is comprehensible. The scarcity of water can be accounted for. The presence of cyanide is explainable. The observed color alteration is also understandable. Each individual characteristic possesses a plausible natural explanation, requiring only minor adjustments to our established models, not their outright rejection. It is the convergence of these anomalies that proves unsettling. The confluence of peculiar features, all within a single entity, the improbable statistical likelihood of this specific combination of traits occurring spontaneously, is what raises concern. The months of November and December promise further illumination. As 3 Atlas re-emerges from behind the sun, terrestrial observatories will capture new spectral data, revealing additional emission lines, more chemical signatures, and providing tighter constraints on its composition. By contrasting its pre-perihelion chemistry with its post-perihelion state, we will ascertain whether solar heating has induced any fundamental shifts in its behavior. Chapter 8. The Anomalous Enigma of the Anti-Tail. The Hubble Space Telescope obtained the most detailed imagery of 3 Atlas on July 21, 2025. The visual evidence contradicted fundamental principles of cometary physics. The photograph depicted a teardrop-shaped envelope of dust, yet the luminosity extended forward from the object, towards the sun, rather than trailing behind. There was no discernible tail extending away from the sun in the opposite direction. This presentation is inverted. Cometary tails are propelled away from the sun by the solar wind and radiation pressure. Consequently, the tail should invariably point away from the solar body, creating the characteristic sweeping appearance associated with comets. However, 3 Atlas displayed a luminous front facing the sun, devoid of any apparent tail behind it. Jav Loeb and his associate Eric Keto authored the sole scientific publication attempting to elucidate this peculiar anti-tail phenomenon. They posited that the forward illumination might be attributable to dust particles propelled ahead of the nucleus by some internal mechanism, though they themselves acknowledged the speculative nature of this hypothesis. There is no readily apparent natural process that would generate a dust cloud oriented in the direction of motion for a typical comet. Other astronomers largely dismissed the observation, attributing the glow not to an anti-tail, but to image smearing caused by Hubble's tracking of the rapidly moving target. The telescope was actively following 3 Atlas through space, which inherently causes background stars to appear as streaks in long exposures. Perhaps the forward illumination was an artifact of this tracking motion. However, Hubble's image processing experts are adept at compensating for such tracking effects. The streaks resulting from tracking are readily apparent in the image, whereas the forward glow is not a streak. It is a distinctly defined area of heightened brightness exhibiting structural characteristics. If it were merely a tracking artifact, it would resemble the stellar trails. This is not the case. Subsequently, in late August, the Gemini South Telescope acquired new images utilizing its multi-object spectrograph. To the surprise of many, 3 Atlas had then developed what appeared to be a conventional tail, a faint, teardrop-shaped appendage extending away from the object in the anti-solar direction, precisely where cometary tails are expected. This implies that between July 21st and August 27th, a transformation occurred. Either the object began to exhibit typical cometary behavior, or our observational perspective shifted sufficiently to reveal what was always present, but previously obscured by the dust envelope. The July Hubble imaging was conducted when 3 Atlas was approximately 4 astronomical units from the Sun. The August Gemini imaging was performed at roughly 2.5 astronomical units. Proximity to the Sun correlates with increased solar heating, enhanced outgassing, and potentially a greater production of dust. It is plausible that a tail had not yet fully materialized by July, and subsequently appeared as the object's activity intensified. However, this explanation does not account for the forward luminescence. Ordinary comets do not exhibit bright halos directed towards the Sun. They possess comas, which are spherical envelopes of gas and dust surrounding the nucleus. The coma can appear brighter on the sunward side due to increased sublimation activity, but it should not manifest as a directional glow preceding the object's path. Another perplexing detail within the Hubble imagery is the extent of the dust cocoon. It envelops 3 Atlas by approximately 3,000 kilometers in all directions. Loeb calculated that assuming a nucleus diameter of 10 kilometers, the dust density at a distance of 3,000 kilometers would be diminished by a factor of 90,000 compared to its density near the nucleus's surface. Such a substantial dilution of dust would typically render it too faint for Hubble to detect. This implies either an extraordinary quantity of dust is being generated, the dust particles possess exceptionally high reflectivity, or there is an unusual aspect to the light scattering geometry. The Gemini images also revealed chromatic variations. Different wavelength filters highlighted distinct structural components. In ultraviolet light, the object appeared more concentrated. In red and infrared spectra, the dust cloud seemed more dispersed. This aligns with conventional dust scattering properties, where smaller dust particles scatter blue light more effectively, and larger particles scatter red light. Nevertheless, it also indicates a non-uniform distribution of dust grain sizes. A population of very fine particles is situated in close proximity to the nucleus, with larger particles located further away. This distribution pattern could offer insights into the mechanisms of dust ejection, suggesting fast-moving small particles and slower-moving large particles, a characteristic comportment of comets. The complication arises with the object's rotation period. Observations indicated that 3 Atlas rotates once every 16 hours, which is relatively slow for an object of its size. A 10-kilometer nucleus rotating at this rate would have a surface velocity of only about 1 meter per second at its equator. This speed is insufficient to eject dust particles into space through centrifugal force. Therefore, the dust must be expelled by gas pressure originating from sublimation. Carbon dioxide sublimating from the sun-facing side carries dust grains along with it. However, analysis of the Hubble imagery suggested that dust particles were moving at approximately 20 meters per second. This velocity, while significantly faster than the rotational speed, is consistent with gas drag forces. Herein lies the intrigue. If dust is being ejected at 20 meters per second due to carbon dioxide outgassing, and if the object is expelling 129 kilograms per second of carbon dioxide, as measured, then the dust production rate must be substantial, likely on the order of tons. Such a prodigious quantity of dust ought to generate a highly visible tail, an extended and luminous feature detectable by professional telescopes. Yet, the July Hubble imagery did not reveal such a tail, only the forward luminescence and a diffuse coma. One potential explanation is that the dust particles are so minute that radiation pressure propels them forward before they can coalesce into a conventional tail. Solar radiation pressure can accelerate microscopic dust grains at a rate exceeding the sun's gravitational pull. If the dust grain size is less than 1 micron, radiation pressure becomes the dominant force, potentially driving the particles ahead of the nucleus. However, this would produce a forward tail, not a forward glow, as the morphology would be incorrect. Another possibility is that the dust particles become electrically charged through exposure to solar ultraviolet radiation and subsequently interact with the sun's magnetic field. Electrically charged dust behaves differently from neutral dust, exhibiting susceptibility to magnetic fields that can lead to focusing or dispersion, resulting in unconventional shapes. NASA's SphereX observation introduces further ambiguity. It detected 3 Atlas as a point source in the infrared spectrum, exhibiting no extended emission, no coma, no tail, merely a solitary dot. In stark contrast, Hubble clearly resolved extended structure. The discrepancy lies in the observed wavelengths. Hubble captured images in visible light, while SphereX observed in the infrared. Dust reflects visible light, but emits thermal infrared radiation based on its temperature. If the dust surrounding 3 Atlas is exceptionally cold, colder than anticipated for its distance from the sun, it would appear faint in infrared wavelengths despite its brightness in visible light. This suggests that the dust is not efficiently absorbing solar heat. It might possess a high reflectivity, deflecting light before absorbing heat, or it could be composed of materials with unusual thermal characteristics. The tail situation is expected to become clearer in December, when 3 Atlas reappears from behind the sun. New observations from multiple observatories utilizing various wavelengths will indicate whether the tail has further developed, whether it conforms to typical cometary tails, or if it continues to display unusual characteristics that deviate from theoretical models. Chapter 9. The 1 in 500 Trajectory Coincidence. 3 Atlas traverses a retrograde orbit, inclined at approximately 175 degrees relative to the ecliptic plane. While this sounds extreme, it translates to the object moving in almost perfect alignment with the orbital plane of the planets, but in the opposite direction. It threads its way through the solar system along the same flat disk where Earth, Mars, Venus, and Jupiter orbit, but with reversed directionality. The statistical probability of this occurring by chance is 1 in 500. Most objects entering our solar system from interstellar space are expected to arrive from random vectors, given the three-dimensional nature of space with no inherent directional preference. If interstellar comets are merely debris ejected from other star systems on random trajectories, they should originate from all angles, from above, below, and the sides of the ecliptic plane, distributed uniformly across the celestial sphere. However, 3 Atlas entered our system in near-perfect alignment with the planetary orbits, deviating by only 5 degrees from the ecliptic plane. While not impossible, this is highly improbable. Furthermore, it is not merely the inclination that is noteworthy. The trajectory brings 3 Atlas into close proximity with several planets. It will pass within 30 million kilometers of Mars on October 3rd. It is projected to pass within a reasonable distance of Venus, and in March of 2026, it will approach within 54 million kilometers of Jupiter. Each individual close encounter, in isolation, is not remarkable. Space is vast, and many orbits intersect planetary zones without deliberate targeting. However, the confluence of factors, the alignment with the ecliptic plane combined with multiple planetary encounters, significantly reduces the probability of a random occurrence. Loeb's calculations estimate the combined odds of all these geometric factors transpiring by chance to be approximately 1 in 500. While not impossible, this level of improbability warrants serious consideration of non-random explanations. If 3 Atlas were intentionally dispatched to survey the inner solar system, an optimal trajectory would involve passing near the major planets and aligning with the ecliptic plane, the region where most of the solar system's significant bodies and potential cradles of life are located. Such a path would be logical for a surveying probe. Critics contend that this constitutes selection bias. We are only observing 3 Atlas because its trajectory brought it close enough for detection. It is possible that hundreds of interstellar objects are traversing the outer solar system on random paths, remaining undetected due to their distance and faintness. The objects we do detect are, by necessity, those that pass near the Sun and Earth. This argument holds validity. Our detection capabilities are heavily skewed towards objects that traverse the inner solar system, where our telescopes are concentrated. The vast majority of interstellar visitors that remain in the outer reaches may be escaping our notice. However, this does not fully account for the specific alignment. Even among objects that pass close to the Sun, most would not exhibit such a precise alignment with the ecliptic. Many would possess high inclinations, intersecting the planetary plane at steep angles. The fact that 3 Atlas is nearly coplanar with the planets is an unusual characteristic, even within the subset of objects we are capable of detecting. There is another intriguing aspect to its trajectory. 3 Atlas is on a hyperbolic orbit with an eccentricity of approximately 6.16. This indicates that its velocity significantly exceeds escape velocity, meaning it is not gravitationally bound to the Sun. It originated from interstellar space and is destined to return there. By reversing the orbital mechanics, astronomers can trace its path backward to its point of origin. These calculations suggest it originated from the thick disk region of the Milky Way, possibly from a star system between 7 and 11 billion years old. This is an extraordinarily ancient origin, predating our Sun and solar system. If 3 Atlas formed around such an ancient star, it has been journeying through space for potentially billions of years. Its prolonged exposure to cosmic radiation, the cumulative chemical alterations, and its sheer age render it unlike any object previously studied. The object's galactic path also provides clues. At its current velocity, adjusted for the Sun's gravitational influence, 3 Atlas was traveling at approximately 58 kilometers per second through interstellar space prior to entering our system. This velocity is consistent with objects belonging to the thick disk population. What is incongruous, however, is the timing of its arrival. 3 Atlas entered the inner solar system in mid-2025, precisely as our detection capabilities reached a threshold sufficient for its observation. The Vera Rubin Observatory commenced operations. The Atlas project achieved full operational status. The SphereX mission was launched. All the necessary infrastructure for characterizing an interstellar visitor was in place. Is this a coincidence or a calculated timing? If an advanced civilization were to dispatch a probe to survey our system, they might strategically select their arrival time. They might wait until the target civilization has developed sufficient technology to detect and study the probe. Their arrival could coincide with the availability of telescopes capable of analyzing composition and measuring trajectories, facilitating a first contact when the recipients are equipped to comprehend what they are observing. While this sounds like science fiction, it is not beyond the realm of possibility. Any civilization capable of interstellar travel would likely possess the means to observe target systems from a distance. They could monitor for technological signatures, such as radio transmissions, artificial lighting, or atmospheric pollution, indicating a civilization's advancement to a certain developmental stage. Earth has been broadcasting radio signals for over a century. Our technological emissions have been detectable by external observers for decades. If 3 Atlas was dispatched in response to detecting these signatures, its arrival timing would be logical. Of course, this scenario necessitates the acceptance of interstellar travel as feasible, the existence of a civilization that has mastered interstellar journeys, their intention to send an object to our system, and their deliberate disguise of this object as a comet. These are numerous assumptions. However, the trajectory itself remains a significant factor, with odds of 1 in 500 exhibiting perfect alignment with the planetary plane and close approaches to multiple worlds, arriving precisely when we developed the capacity for detailed study. The encounter with Jupiter in March 2026 will be a critical juncture. If 3 Atlas maintains its predicted path, passing Jupiter at the expected distance without deviation, this would support the natural explanation. Orbits governed solely by gravity are predictable and devoid of surprises. However, if deviations occur, if the trajectory alters in ways unexplainable by gravitational perturbations from the planets, then a serious problem arises. We would then need to account for what altered its course, and natural explanations rapidly become exhausted once gravity and outgassing are ruled out. Chapter 10. The Approaching Verdict. The Judgment Draws Near. October 3rd, 2025. This is tomorrow. The high-resolution imaging science experiment, HiRISE camera, will be directed towards 3 Atlas as it passes at a distance of 29 million kilometers, achieving a resolution of 30 kilometers per pixel. This level of detail should be sufficient to differentiate the nucleus from its surrounding dust cloud, enabling measurement of its surface area and constraining its actual dimensions. If the nucleus is confirmed to be 5 kilometers or larger, the statistical improbability becomes impossible to disregard. We should have detected thousands of smaller interstellar objects prior to encountering one of this magnitude. The natural explanation would then necessitate an escalating series of highly improbable coincidences. ESA's Mars Express and ExoMars Trace Gas Orbiter will conduct simultaneous observations utilizing spectrometers and cameras, employing multiple wavelengths, instruments, and perspectives. Collectively, the Mars spacecraft will provide the most comprehensive examination of an interstellar object ever undertaken by humanity. Furthermore, a search will be conducted for precursor probes, objects traveling ahead of 3 Atlas that might reach Mars while we are observing the primary body. HiRISE will scan the surrounding space. If any unexpected entities appear, if multiple objects manifest instead of a single one, the entire discussion will be fundamentally altered. Subsequently, a waiting period ensues. 3 Atlas will disappear from Earth's view, passing behind the Sun in late September. We will lose visual contact. The object will reach perihelion on October 30th, its closest approach to the Sun, concealed from our telescopes by 150 million kilometers of incandescent plasma. This represents 2 months of obscured observation, a window during which any event could transpire unnoticed. Trajectory adjustments, probe deployments, fragmentation. Whatever occurs during this period will only become apparent in December, upon the object's reappearance. December 3rd is the anticipated date for ground-based telescopes to reacquire 3 Atlas. Amateur astronomers worldwide are making preparations. Professional observatories are scheduling observation time. All parties are eager for the initial observations of the object as it emerges from behind the Sun post-perihelion. Crucially, all post-perihelion data will be rigorously compared with pre-perihelion information. Has its luminosity changed? Has its outgassing increased or decreased? Most importantly, is it positioned where calculations predict? If 3 Atlas reemerges on an altered trajectory, if its orbit has changed in ways that cannot be attributed to gravitational interactions with the Sun and planets, this would constitute evidence of propulsion, evidence of technology. At that juncture, even the most skeptical individuals will be compelled to consider alternative explanations. The chemical analysis will also yield further insights. New spectroscopic data in December will reveal whether the nickel without iron signature persists, if the carbon dioxide dominance continues, or if novel emission lines emerge that were absent prior to perihelion. Thermal processing due to solar heating could alter surface chemistry in detectable ways. If the object fragments, this would actually support the natural comet hypothesis. Natural comets occasionally fracture near perihelion due to thermal stress. We have witnessed such events with comets like Shoemaker-Levy 9 prior to its impact with Jupiter. Fragmentation would be considered normal unless the fragmentation appears controlled. If multiple pieces separate cleanly and proceed towards distinct destinations, then fragmentation transforms into deployment. The Jupiter encounter is slated for March 2026. NASA's Juno spacecraft, currently in a polar orbit around Jupiter, may have the capability to observe 3 Atlas as it passes within 54 million kilometers. Juno is equipped with cameras, spectrometers, and particle detectors, instruments designed for Jupiter studies but potentially adaptable for characterizing this visitor. There has been discussion regarding Juno's ability to maneuver for a closer observation. The spacecraft possesses limited fuel reserves, and its mission has a predetermined end. Diverting this fuel to pursue an interstellar object instead of continuing Jupiter research would be a contentious decision. However, should the October and December observations reveal genuinely anomalous characteristics, the scientific rationale for reorienting Juno would become compelling. ESA's JUICE spacecraft will also attempt observations in November, although the data transmission will be delayed until February 2026 due to communication constraints. JUICE is positioned further from Earth, on the opposite side of the Sun, utilizing its antenna as a heat shield, which limits data transmission until its orientation is adjusted. Consequently, we are compiling observational data across multiple months from a variety of spacecraft situated at diverse locations within the solar system. By spring 2026, we will possess the most extensive dataset ever assembled for an interstellar object. This dataset will either validate 3 Atlas as an unusual yet natural comet originating from another star system, or it will compel us to seriously entertain the possibility that we are being visited. The scientific community is actively preparing for both eventualities. Within the private circles of astronomy, discussions are underway concerning the hypothetical procedures should definitive signs of artificial origin be confirmed. Questions arise. Who would be tasked with the announcement? How can such extraordinary assertions be rigorously validated before a public disclosure? Furthermore, what would be the ramifications for planetary defense strategies if additional such entities were to be detected? The absence of a formalized protocol stems from the fact that this particular scenario was never seriously anticipated. Existing SETI protocols are primarily geared towards the detection of radio transmissions and deliberate communication signals rather than physical objects that bear a resemblance to comets. The closest established parallel can be found in the protocols for announcing the discovery of extraterrestrial life on celestial bodies like Mars or Europa. These involve meticulous verification, thorough peer review, and multiple independent confirmations preceding any official statement. However, these established procedures are predicated on the assumption of ample analytical time, often spanning months or even years. The object designated 3 Atlas is currently traversing our solar system and is on a trajectory out of it. If we are to conduct a thorough investigation of this phenomenon, critical decisions must be made with expediency. Some members of the scientific community are actively proposing an intercept mission. This would involve dispatching a compact exploratory probe to rendezvous with 3 Atlas before it exits the solar system beyond Jupiter's orbital path. Such a mission would aim to capture high-resolution imagery, obtain samples of its outgassing plume, and take direct measurements of its magnetic fields and particle emissions. The primary obstacle is the constraint of time. Even a swiftly dispatched spacecraft would require many months to achieve a successful interception. By the time authorization and funding were secured, and by the time the probe itself was constructed and deployed, 3 Atlas would have long since departed. Interstellar objects travel at considerable velocities. The opportunities for study are measured in weeks, not years. This is precisely what renders the time frame between October and March so exceptionally vital. This represents our sole chance, our singular opportunity to gather crucial data on the third verified visitor from beyond our solar system before it recedes back into the vast emptiness between the stars. Following the month of March, it will have traveled too far and become too faint for any detailed observation. We will observe its diminishing presence in the distance, extracting every possible piece of information from the data we manage to acquire, and then we will wait. We will wait to ascertain if our analysis reveals conventional explanations for all the observed anomalies. We will wait to see if further interstellar objects arrive, exhibiting comparable characteristics. We will wait to determine if the statistical likelihood of a natural origin either resolves itself or becomes more pronounced. And we will ponder, even if the data ultimately points towards a natural explanation, even if every unusual observation finds a conventional justification. We will still ponder because a 60% probability of technological origin inherently implies a 40% probability of a natural origin, and 40% is not zero. The universe has presented us with unexpected revelations in the past. Phenomena such as black holes, dark energy, exoplanets, and gravitational waves have each demonstrated aspects that were initially unpredicted and remain only partially understood. 3 Atlas might represent another such surprise, perhaps something natural, yet so exceptionally peculiar and unforeseen that it compels us to revise our current models and broaden our comprehension of what is physically possible. Alternatively, it could indeed signify the most profound discovery in the annals of human history. The first unequivocal confirmation of contact with technology originating from beyond Earth, providing tangible evidence that humanity is not alone in the cosmos, proof that other civilizations exist and that some of them have attained the capability for interstellar travel. The answer is imminent. The data is progressively arriving. October 3rd, December 3rd, and March of 2026. 3 specific dates that hold the potential to fundamentally alter our perception of reality.